Hello, um, welcome back. We're here for the third talk, and I am really of this track on this screen stage. I just wanted to remind everyone that then there is the closing note on the main stage, and I'm very happy to welcome Filip, which is a senior software engineer in Google Cloud in Warsaw, Poland. And it will present the challenges of running a reliable, scalable, and easy to manage service in cloud. And now Google Cloud Platform Autoscaling and workload management products can help. And without further ado, I welcome Filip to the stage and let you take it away.
Hello, good talking to you. So let's get started. So first of all, let's talk about how you would want to run your service in cloud. So obviously you have many goals. Some of them are unrelated to cloud, but let's focus here on the ones that Google Cloud could help you solve with the management capabilities. So when you think about how you would like to run your application, your service in cloud, there are a few things to consider. First and foremost is reliability, because whatever features you have in your service, whatever capabilities you want to provide to your customers, if you don't have sufficient reliability, then everything else is kind of pointless. So you can also think of reliability as kind of the first feature you think about before you keep adding additional features. So here, as part of reliability, it will be heavily focused on that later in the slides, but we will focus mostly on handling failures of various sorts and recovering from them ideally automatically. We'll also look into how changes in demand for your service, so changes in traffic, can affect your service availability, as well as any operations you are making to the service, so updates of a version or any other operations. So having reliability as one goal is great, but then obviously you don't want to overpay. So ideally you pay only for what is needed at a given point in time. So you don't. That's the kind of the selling point of cloud, right? That you have this elastic capacity. You can pay for only what you use, and with that, like you actually have to make a little bit of effort to configure your service in a way to take the best. Uh, uh, Best benefit of that. And then finally, you don't want to have too much toil, operational maintenance cost by running your service in cloud. So everything that could be automated, you likely should look into doing so too. That will pay back in the future. So let's start by looking at some extremes. They are not very practical. They are just for illustrative purposes. So obviously, if you want to focus on just maximizing reliability at any cost, then you replicate your service as much as you can imagine, right? So across many failure domains, many machines, many availability zones, many geographical locations. You provision much more capacity that you actually need. So you over provision the size of your service to handle any unexpected traffic changes. And then finally, you don't touch anything, because as soon as you touch, you introduce additional risk. So that's obviously not practical, and it's way too expensive, way more expensive than it could get. And even though it has so many downsides, it's still never 100% reliable. There are many service specific things you could do that will actually increase your reliability much more than those crazy examples here in this extreme. Then finally, something slightly more practical. So in very few cases it actually makes sense, but probably 90+% of cases it doesn't, or even more, is to have something tailor field for your service, right? So especially if you run like a huge service that is very custom in terms of the the characteristic of how the demand is handled, how the service behaves. Sometimes it makes sense to build something custom, so have a completely custom solution for managing this application in cloud. This is obviously very expensive in terms of engineering time you have to invest into building that and then maintaining. So most of the cases, like a great majority of the cases, is basically running a generic solutions that could be tweaked to fit your use case versus just building it from scratch. So again, not very practical. The last extreme is sometimes very practical, but so for cases like a very simple applications that do not require any kind of powerful options to use out of the cloud offering. So if you really don't need a lot of the outside of the basic set of requirements for running your service, and especially if you have a stateless service, then you would be probably better off using a higher level service cloud product, like platform as a service type of product, where you have an opinionated runtime when you don't have that much control, but at the same time you have a lot of the maintenance and problems solved automatically without much of your even without configuration requirement from you to some extent. So it's kind of out of the box solution for those use cases. But for this presentation, we'll focus on cases where this will not work for you, which is a lot of cases where you actually have requirements that may make Google Compute Engine or GKE the solution for you. So just to summarize, your goal, just to avoid the extremes, your goal is to find a balance between those two goals, right? So you'd like to meet those reliability goals by running your service in cloud, but at the same time, reduce the cost both in terms of resources and operational cost in maintaining the service. But just to be precise, what do we exactly mean by reliability? It's as I mentioned, it's a huge topic. So one way to talk about reliability is by going through various failure modes, failure scenarios. So things that could fail when you run a service in cloud or anywhere, but we will focus on public cloud and GC and as an example here. So all the scenarios I will be talking about will use virtual machines and Google Compute Engine as an example, but kind of the principles here are the same across other products where you can manage your service. In particular, Kubernetes or Google Container Engine is one of those other products. You could apply those principles. So let's start. So you start small, obviously. You prototype, you build your first application, first versions. You don't. It's not yet live. You just have it in some staging environment. You want to make sure it's actually functional and ready to be launched publicly. And finally, when you build up and you are ready to open it to the external world or to your internal customers, but basically getting it to production environment. What you want to do as a first step is replicate across multiple machines. So we are seeing on the right side here a group of virtual machines, which are running obviously on underlying physical infrastructure. And the reason why you want to replicate is kind of twofold, right? First of all, you would like to be resilient to issues which are could happen independently to each of those instances. Those issues, those unexpected downtime can be caused by either your application having any issues, so having things like crashing, error rates increasing, or any other reasons for your application to misbehave. And so that would be kind of on the software side, on your application side. But there could be also sometimes some underlying hardware issues. So the actual physical machine hosting your virtual machine could have an issue, and from that's possible. Those are all physical machines that could break from time to time. So this other kind of cloud cost type of failure is also something you have to think about. That's why using more than one is definitely a good idea to make you ready for that. So in this picture, you can see when you are losing some part of your capacity, that could result in a degraded performance of a service, obviously. So either some of your customers are getting those errors, or overall the service is overloaded, so the customers are experiencing higher latency or some other characteristic is degraded. So the way to kind of recover from that situation, from that scenario, is to enable automatic repair of those machines. So this is the feature we call Autohealing. So here the way it works is that it looks at the health of each of those machines and can automatically recover them by recreating kind of from a fresh image. So whatever kind of degradation that happened, or like a crash, a bug that happened there, like you can basically reboot it from a clear image and give it another try. So that would be probably the first thing you would do manually, and you can obviously automate it in cloud to just happen, make it happen as soon as the problem is detected. So yes, so the next type of thing to consider is that every time that a machine gets unhealthy for whatever reason, either it crashed or there was some other issues on the networking side between machines, then you don't want to send any traffic to this machine, right? So this is what load balancer is handling. So your customers are reaching your service through a load balancer, and it is responsible for first of all balancing the traffic, meaning sending a proportional amount of traffic to each of the instances to not overload any of them and try to keep everything equal. But it also is responsible for making sure that if something is unhealthy, this endpoint that is unhealthy is not being used for serving traffic. So load balancing takes care, just to summarize, load balancing takes care about not sending traffic to unhealthy VMs, and in the background, Autohealing takes care of bringing those endpoints back to life. So we've just discussed the unavailability of machines at kind of at a single machine level, so losing one or few machines. But it could be also possible that you could have a complete zonal blackout. This could happen again because of something in the application layer, or a dependency of your service could be down in a given zone, which means your service is unavailable because of that dependency is lost. Or it could be your cloud provider having issues in one particular zone. Zones in every cloud provider are exposed by following this principle that all the cloud providers try to keep zones as independent as possible in terms of limiting failure domain between them. So a failure of a single zone shouldn't affect the zones next to it, meaning that if you are able to which means you are able to takes advantage of that and use more than one zone to prepare for that. You can do it manually, so you can just deploy multiple groups of machines in multiple zones, or you can use a ready solution like regional managed instance groups, which automatically replicates your application across multiple zones. So you can see here your machines are equally spread across each of the zones, and then if there is any issue with any of the zones, because zones are built to be independent, you will be ready to serve from the remaining two zones in this example. And again, similarly to Autohealing and a single machine failure, load balancer takes care about not sending traffic to the unhealthy endpoint, while the lower layer compute tries to handle the failure itself. And here you can do multiple things. So let's start with autoscaling. If you have automatic scaling enabled, then the capacity that has been lost would be recreated in the remaining two zones. So for the time being, where you just lost those 3 machines in this example, but we didn't yet provision those machines in the healthy zones, your service will be obviously serving with fewer machines, so it could be overloaded. If you were running hot before the outage, you will be likely overloaded, but it should again recover automatically from that by getting VMs in the healthy zones. To avoid this intermediate overload that I just mentioned, you can over provision your capacity. So in the previous example with 3 zones, that would mean that would be 50% more of the capacity would be needed to be ready for an issue like that. And we can go over a simple example. Let's say you need 10 VMs to handle your traffic. If you over provision by 50%, this means you need 15 VMs in a region, so 5 in each of the 3 zones. So if any of these 3 zones goes down, you're losing 5 VMs, so you're left with exactly what you needed, which is 10 VMs. So you can read more details on that in our public documentation for for other scenarios, especially for how to apply it to auto-scaled groups, where you want to have both this over-provisioned capacity and this reactive auto-scaling on top to get kind of both of those behaviors at once. And since I mentioned auto-scaling already, let's look into what auto-scaling actually could do with in terms of preparing you for traffic changes. So that should be pretty straightforward already based on the previous examples. But if your traffic receives more traffic than you anticipated, it will be overloaded. On the other hand, if you over provision too much and just create a very big group, very often you are just wasting resources. You are paying way too much for what would be needed to serve this traffic. So this is where auto-scaling comes as a way to dynamically adjust this capacity. The way you configure auto-scaling is by setting a utilization target. So here, as an example, I used CPU utilization. So when you're running at the target, which is here 60%, that's the target means this is the level of utilization that your application is healthy with. So it can serve the traffic with desired latency and other properties. So when it's overloaded, so when the actual utilization is above the target, auto-scaling will add additional machines. And when the average utilization goes way below the target, then it will remove the unnecessary machines so that the traffic can rebalance and kind of run as close to your 60% target as possible. Here, the resolution is kind of a single instance, right? So if it's possible to remove an instance without getting the utilization above the target, this is what would happen. And finally, the operation that can cause a lot of risk to your service running live in production is any changes, right? So you're rolling out a new version of your binary across your machines, and this is a risky operation. The new version can crash. It could serve errors. It could have many other misbehaving properties that you don't want to see kind of spread to all of the capacity you're using, right? So you don't want to go with update too fast, especially don't want to apply it to all instances at once. You don't want to have any maintenance windows where you kind of take everything down and bring it up with a new version, because obviously during that time you are not serving at all. So what you actually want to do is to do a very gradual rollout where you can either use a policy where you keep replacing an instance one after one, or with some budget specified, so not more than 5 at once or whatever is your constraint, and keep replacing them and wait until they get healthy and only then progress to the next instance. Or if you don't want to kind of reduce capacity at all, you can do an update in a version where you actually first add additional capacity, wait for this additional capacity to be ready and healthy, and only then you remove an instance with a previous version. So all of those modes are available to you if you would like to have a safe rolling update across your pool of machines. In terms of how load balancer, kind of the point of view of the load balancer of that operation is that, again, you're serving a production traffic. This is a live service that you are modifying here. So the first thing you want to do for an instance that is going to be updated is to stop sending new traffic there. The existing connections can continue to operate, so you wait for active session to complete. There is some timeout, but you configure it in a way to kind of make sure all of that can finish before you terminate, and this maximizes this minimizes the number of disruptions you will cause to the end user. And then if you have a completely drained instance, you can do the actual update, change the version, wait until it is healthy, and then reconnect it back to the load balancer to let it receive new traffic. So looking at all of that combined, like you can use all of that on a single abstraction called regional managed instance groups. You can handle single failures, zonal failures, changes in demand, as well as safe updates. And going one step further, you can apply the same logic to go even beyond the region, and especially for the cases where you have a service that is global in nature, have customers across the world. You can have a global load balancing IP that is able to, and then the global load balancer is able to send your traffic to different regions. Each of them is configured as we just discussed, so you get this additional level of multi-region failure modes. And then for the rest of the presentation, I will quickly go over like an example of what it takes, kind of look into the kitchen, how what it takes to build an autoscaling cloud feature like the one I discussed. So now let's imagine we are kind of from the point of view of a Google engineer building a service like that, because I think that could be an interesting thing to see. So this is another way to look at the autoscaling problem. So you have a demand that is changing in time. So this is the blue line. And if you don't use autoscaling, you have a fixed capacity. This is the red line in the middle. And autoscaling can help you not only with cost savings, so not paying for what you don't need, but it can also provide you higher availability than a fixed capacity, since it can go way beyond what you would be comfortable, configuring as fixed capacity. But the life is not that simple. The real life is much more complex, and applications usually are not able to follow the demand that closely. And the reason for that is very often the long initialization time, meaning that if you just react to so on the horizontal line we have time, and then on the vertical line axis here we have number of VMs. So as you can see here, if you're just reactive to the demand, you will provision the virtual machines, but the actual application will take few minutes to get healthy and to actually start serving traffic. So the load balancer will actually start using this new instance sometime after it was created, and this depends on your application, how much data you need to load to memory from some external data sources to actually be fully serving. It could also your software may just need some time to initialize. And to solve that problem, what you would ideally want to do is to scale in advance, meaning predict the future, start creating instances, minutes or tens of minutes in advance, and then get them be ready for serving just before the demand is ramping up. So again, this is another type of a problem where you balance cost and availability. This is very different workload by workload, and we'll get to that. But just to not be not use only fake pictures, let's look at the actual picture from one of our real customers. So here again you have time on the horizontal axis. This is about a day, so this is like a morning spike and the evening spike, and then on the vertical axis you have obviously number of instances they are using to serve. And here we are talking about hundreds of instances. That's why you have such a resolution. So the black line here is what they need. So what they would ideally like to run at 60% utilization. This is the kind of the happy utilization for this application. And so the first obvious thing to do is configure autoscaling to run at 60%. But this is the red line. So you can see the red line is very often significantly below the red line, which means the service is overloaded. So they don't have enough capacity in time when they run at 60% because of the initialization time, which is not that crazy. It's 10 minutes. There are bigger numbers that people complain about, but 10 minutes is what this example has. So what they've been doing previously is that they've been significantly over provisioning here with autoscaling, meaning they were lowering the target. So they were running not as hot. They were running at 35%. This is the orange line. So as you can see, it helped them avoid crossing the demand line, but it's also pretty obvious that it was much more expensive for them to do so. And even so, there were places where you can see here where it was still not good enough. So with predictive autoscaling, as you can see here, you have three versions of autoscaling enabled here. One is predictive at 35%. So this is just enabling predictive on the reactive algorithm they had with the same utilization. It's way away from the black line, so it gives you a lot of kind of safety buffer here. Which means that they could actually tweak it further and not only enable predictive autoscaling but also increase the utilization target. So the final target they use is 45% in this example, which means that they get like 29% of reduction in time for when the service was overloaded, which is huge, and it cost 5% less, right? So they got kind of in this balance problem, they got actually two of those positive, right? Not only reduce cost, but have a significant reduction in availability. So this is an example of real life example of how you can use predictive to tweak your service and gain availability by reducing the cost. And okay, so how did we do that? So obviously we used machine learning to predict the future, but it's not as easy as it may sound. So as you think of machine learning or basically machines making any decisions, you always have to ask yourself a question: what is like kind of the worst that can happen? What is the consequence of a bad decision? You want to be prepared for that. And obviously, on this is a spectrum. On one hand, you have those problems that are not that significant if you make a mistake, and so this is some image classification of that is not fundamentally critical to anything. It can result in some funny results. But on the other end of the spectrum, you have a more serious applications when a human health is potentially at danger if you make a bad decision. So then the obvious question is like, okay, where cloud ML lands, and obviously it's in between. I would say a little bit to the right here. So it's a serious problem when you make a really bad decision in cloud. It can cause a production outage. It's not obviously as bad as things to the right of that, but your people running things on cloud really care about those things being up and running. Their businesses often depend on availability of those. So the decisions made by cloud should be really safe. But it's at the same time, it is obvious it will not work for everyone. It will never be 100% correct. So the first thing you have to do is define the measurement, measure metric, measure the metric of success. So what it actually means for your model to be right and how wrong it was, and then evaluate on real data sets. But you cannot just pick any representative sample, because unfortunately there is no such thing as a representative sample of cloud workload. People run so many different things in cloud that it's not possible to just have a good representative sample. So the thing you want to do is actually run over all the history of workloads you have available to you. And for that, you actually would like to optimize for not only get as high as possible, but to be ready for the cases. Just like by design, be ready for the cases where you are wrong, because you will never get it to 100%. So even if it's 0.1%, those customers are they are unlucky, but they kind of don't care, right? They are just they have a bad day, they have an outage, and at Google scale, this is actually a very big subset of users that will have an outage when we are talking even a small percentage here. So what you do is you first of all try to get your model to as high quality as you can get by analyzing a huge data sets. So ideally all the workloads and big time horizon. That's a lot of that. Those are a big pipelines that you need to run to actually get crank all those simulations. You want to analyze the outliers, try to understand how you can improve on those cases where you are currently failing, and even if you get those two steps, then it's, in my opinion, the last is the most important ones. You want to build, defense in depth. So you want to have a set of checks and, human written rules and other sanity checks to protect against those very rare cases where it actually will go very wrong. But how do you do that when you also want to follow the privacy obligations you have with your customers? So you cannot just look at user data, and there you have basically two options here. One option for you is to, and you do both. So first of all, you look only at anonymized data, and by look I mean you write pipelines that simulate using anonymized data, and you always use aggregate, so you never analyze any single case to match, right? So it's only about getting the overall score improved. And then finally, you can work with few customers, and this is super helpful for projects like this one. Work with few trusted customers as a pilot program to get their first-hand opinion and actually do a deep dive into particular workload. But even with that, you then launch a product like that, you are out of the pilot program, and it's up there, right, for people to use in cloud. And the product like that is not that easy to get, to earn trust, because people, usually our customers, are not domain experts in ML, and often not even in with public cloud, right? They are used to the previous ways of running services. So it's very hard to gain to earn this trust. And the best way, I believe, for that is to let the customers kind of judge themselves about how effective this given feature, like the predictive scaling, could be for their given use case, right? And here, good UI and various simulations we could show them is I think the best approach, because it shows for a given use case how it would behave, and they can judge themselves. And ideally, anything that happens in cloud should be understandable by the customer themselves. So there should be enough, logs and tools to analyze what actually happened, which again builds more trust and gets more of that. More of that trust. It's sometimes okay to kind of lower. Have a second opinion from a customer support team to help customers analyze those cases, but ideally, as I said, is when it's a kind of self-service type of judgment. Okay, and finally, the key takeaways from building a service, kind of a cloud product like that, a cloud capability like predictive autoscaling, is that, first of all, like, we have to focus on gaining this trust and earning customer trust, because without that, no one will use the product they are afraid of, or they try it and they got disappointment from. And then even once you get this trust and get your customers to trust the machine learning to take control over their workloads, they would it's easy to lose it, right? Like, if you make a one big mistake, cause one outage for one customer, this customer is very likely not ever using either your product or maybe even your other products as a consequence of that, right? So this is a very, very sensitive topic, meaning that you want to really think of it very early through your testing, evaluation, and design phase, to actually build a system with a lot of defense in-depth checks all over the place. And finally, you can engineer a lot as usual, as you probably know, right? Most of the problems here is just a matter of good engineering solutions, good designs with enough kind of user-centric approach to them, meaning making sure the decisions are safe and understandable. And if you get those two, then you should be good with a product like that. All right. So thank you very much.
Thank you so much, Filip. I found that super interesting, and I hope the audience found it too. So thanks again. I just want to remind everyone that we really care about your feedback. So please, if you can go on the link below to gather some feedback. There are also some interesting prize that will be raffled between all participants of the feedback form. And also, this was the last talk for the green stage. So thanks a lot, Filip. And I also wanted to remind that we will have the closing keynote at the main stage in a few minutes. And in the meantime, if you want to join special chat, or you can just hang around the other stage and then come back to the main stage. And with that, I will see you all in the main stage. Thanks again. Bye again, Filip.
Thank you.